So we talked about resampling, and we talked about the bootstrap, and we talked about cross-validation, where you're splitting your training set into different sets in order to validate your results. So one idea that might occur to you is, well, look, we have all these different subsets of our training set lying around. Why don't we train different classifiers on each one and combine their results? Right? So instead of trying to use it to validate one particular classifier, why don't we just make a whole bunch of different classifiers? And so the question that you need to answer is, well, look, does it actually make sense? Does it work to take a bunch of not very good classifiers and combine them? Will it actually get better? And the answer is not trivial to find out, but it was found out, and the answer is yes. Okay. And so you can average the results of different models, and you get a couple of benefits. One is the strength will go up, the classification performance will be better, and you can drive it up by design. But more importantly, perhaps, is more resilience to noise, and so you reduce the chance of overfitting by having a bunch of different classifiers all work in tandem. Okay, so why wouldn't you do this? Well, there's two reasons. One is it's time consuming, right? Obviously, training a bunch of different classifiers is more expensive than training just one. But also, the behavior of your model becomes difficult to explain, right? When you have a whole bunch of different models all sort of voting on the answer, it's difficult to take some intuition for what logic is actually being applied. And so remember we said just like one rule was easier to understand than a big set of rules, one decision tree was easy to understand, a big set of decision trees is perhaps not. But that's not going to stop us from doing it. Okay, so the idea here is that there's this wisdom of the crowds model. Well, it works when you're talking about these digital artifacts as well, these generated models. All right. All right, so how do we actually do this? Well, one technique is called bagging, which is a portmanteau of bootstrap and aggregating. And so the idea here is to draw your in-bootstrap samples, retrain the model separately on each sample, just as we described, and then average the results. And so if you're talking about a regression problem that we haven't gone into detail yet on, then you would actually literally just average the results. If it's classification, where you're only picking a discrete class label, then you do a majority vote. Okay. And so this works really, really well for overfit models. It resists overfitting because it decreases variance without changing the bias. So without moving the answer around, right? It just shrinks everything to that answer. And if you remember, we put up that plot where high variance tended to mean overfit. It means that you're specialized to the training data and you're very sensitive to the training data. Okay, but it doesn't help much with models that do have a high bias, with wrong models. And you remember, high bias, low variance models are more or less insensitive to the training data. And so all that you're doing with bagging is taking different permutations of the training data. So if you're not getting a good signal out of the training data at all anyway, this isn't going to help much. Okay. So another technique is boosting, exemplified by this algorithm ADA boost. Okay, so here, instead of selecting data points randomly with the bootstrap, you want to favor the misclassified points on each step. All right. So take a bootstrap sample, retrain a model, see what inspect the mistakes that the classifier made, okay, and recompute the weights for the next round of bootstrap, giving extra weight to the example data points that your model got wrong. Okay, so let's see what this looks like a little more precisely. Okay, so for each step t, we've got a vector of weights, which represent the probability of selecting example I in the sample. So that's this d. So d at t, d of I, is the probability of selecting I in the sample. And these are initialized to equal probability, to uniform probability. Okay, and then x and y, x sub I and y sub I are your record and your label. Okay, I've been saying data point, example, and record, I think, sort of interchangeably, which probably isn't all that helpful, but bear with me. So h sub t is the trained classifier at step t, using a sample drawn according to the weights D. Okay. Now, compute the error by adding up all the weights for everything that was misclassified, or this epsilon, I shouldn't say error. Compute this epsilon by adding up the weights for everything that was misclassified, and that's what this incantation is down here, right? So this says for the model h sub t, apply it to x sub I, where it's not equal to, where the classifier tells you something different than the actual class label, then include it in the set and add up all the, add up all the d's for those. Okay. Then compute what's called the odds, which is the odds given a probability is that probability over 1 minus that probability. Okay. So compute the odds of misclassifying, and then weight those values, those misclassified values, by the odds. Okay. Oh, excuse me. You're going to that's not quite right. You're going to this is a value between 0 and 1, right? And so this gives lower weight to d of I, and you're only going to apply this function to the ones that were correctly classified. And all the other weights, you just leave alone. And so this isn't, I didn't put that data, in an attempt at clarity, I didn't include the entire expression. That may or may not have been a good idea. So this is only applied to the correctly classified examples. Okay, and then there's actually one other step that I also removed in an attempt at clarity, which is you need to normalize all these down, because what you've done now is taken a set of weights that normalize to probabilities, they add up to 1, and you've just adjusted some of them down. Well, now it's not going to add up to 1 anymore. But that's okay because you know the relative weight, so you need to renormalize all this. And so it's a pretty simple step, but I find when you sort of throw a divide by z in here, it gets confusing, so I just wanted to explain it this way. Okay, and then that gives you your new weights for the next round, and then you repeat this process. Okay, so a question I want to ask about this, though, given our appreciation for big data and for scale-out solutions, is the difference between bagging and boosting. Well, I guess I should probably promise you. So boosting has a bunch of nice properties, and it's a very, very successful algorithm. And one thing that's especially cool about this is that it's a meta algorithm, right? It works on anything. It doesn't say anything about what this classifier needs to be. It could be a decision tree, it could be any other method you might come up with, right? All it does is affect the data you use to train the classifier at each step. And so this is very, very general and very, very powerful. Okay. And because of this weighting, it actually does sort of start to zero in on the mistakes that are made, giving more and more weight to the errors. And so you can sort of imagine intuitively that the strength of the classifier is going to get very much better and better over time. So that's well and good, and it works. But it has a disadvantage with respect to really big data relative to a simpler approach, just as bagging. And so that is, it's inherently sequential, right? We have this for each time step, the weights at time t plus 1, at step t plus 1 depend on the weights at step t. With bagging, we can just go wild in parallel and do all of this at the same time. Okay. So that's something to keep in mind that you don't see quite as often in the discussions of these various methods, because they tend to focus on the mathematics involved in the sort of performance. But when we keep in a data science context, we need to keep in mind that we're going to be working on very, very large data sets at times. And so a slightly worse performing but easy to parallelize method can win. All right.